Hi, and welcome to this new series of videos about misconceptions. And it's really motivated by the fact that reading some of the papers, it seems like there are some myths that have been taking root in our field, and they look okay. Some of them were perfectly correct some time ago when the materials were not the same as they are today. And I thought I'll share with you some of the things that are crossing my mind. Of course, if I'm wrong, please send me an email. So really the one that I wanted to discuss today is appearing really in loads of papers, and it's the idea that there is one thing you must really make sure is that the mobility mismatch doesn't exist. And really, if you go back, the source is based on a paper from 2005 by the group of Paul Blom. And really back then the materials were such that there could be huge differences in mobilities. And you can see here the differences are really, when they are small, they are more than order of magnitude. And at the same time, there was some indication in the literature that we published that you can't really consider this as a standalone process, because in solar cells everything is entangled, and especially at the time we were discussing that issues of space charge and extraction are strongly entangled with recombination. So you really have to consider both to know what's going on. So really the main message of this paper is that of this presentation, of this slide, sorry, is that the paper that was published in 2005 was perfectly okay, because these were the materials we were interested in. Mobility mismatch was 3 orders of magnitude, and that was really a disaster. But let's see why this is not so general as we try to suggest roughly at the same year. In the following slides, I'll try to explain or demonstrate that losses and transport and space charge are all entangled. And I'll do that using hand waving and water splashing. And we'll start with a picture where this tab is going to be our solar cells. We will have a constant excitation source coming from the top here. The tab is flat, and there is an extraction barrier here, so the tab can fill up. And the question is, are we running this tab in open circuit or short circuit? And let's see. So we open the water flow, and the tab is filling up, and it looks so far that no water is coming out. So what is the situation? And once it's filled up and we are having loads of fun, at this stage what we discover is that the water now are splashing outwards and are flowing freely to the right. So if there is a free fall and no resistance, we are at short circuit. So this is really a short circuit current flow. And now we'll see what might affect this bathtub or water cell in terms of losses and space charge. So the first thing we want to do is to reduce the extraction barrier. So we won't need to accumulate so much water or charges in the bathtub. And you all know that having a high density is not always great, so we want to reduce extraction barriers as much as possible. So in this tab we are making a tiny hole here at the bottom, and you see here we are filling the tab, and once it's slightly filled, everything can come out. And the short circuit now, you can convince yourself it's the same short circuit as before, because everything that comes in goes out. That's the meaning of steady state. So now let's add some space charge or something that will disturb the water flow or the current. And this is our friend from before. And the question is what will happen when we have this disturbance in the flow, not in the force, mind you. And what will happen is that we'll have some water accumulation because the flow is slower and it really interferes with its flow. But besides that, nothing will change. Everything that comes in still goes out. So really, this space-taking charge has no effect on the efficiency of extracting current from the bathtub. And now we are getting to the other side of the entanglement. Remember we said space charge and recombination losses are entangled, so we'll add some losses, and in this case the losses are some holes at the bottom that we are losing water through. So again we'll open the tab, and we see that now because we are losing some of the water or some of the current on the way, the water that's really flowing rightwards is now smaller. And this is really the effect of losses. And now we come to the stage of entanglement, and we'll add our happy friend into the equation. And again, we'll see what happens to the water level. Just as before, it is going up on the left side, and a higher water level obviously generates a higher loss current. And if we are losing more through the holes, we are extracting less from the other side. And now you could say that the space charge is creating losses. But this is not true as we've seen so far, because really this entanglement is what's affecting the device. So if you don't have meaningful losses, then the space charge or this guy won't do anything. So that's the message right from his mouth. Now moving to the real devices, let's look at what would happen in devices through what we could control or modify within these materials. Unfortunately, many times we would like to control, but really this is done through trial and error, and some sense of control is involved. So really the first thing which is relevant are the mobilities, as our first slide indicated. And the important thing to note is that really what is at the essence of all this discussion is that the rate of extracting the charges out of the device is really limited by the slowest carrier. On the other hand, if the recombination depends on the two charges meeting each other, then the recombination rate is limited by the fast charge. And from this you might say that we have this notion of balancing fast and slow charges. So in principle, this is a good idea to balance them. The only question, are we losing anything if we are not really balancing, or is this really the thing that we should focus on? And this is just to summarize the 2 points. And indeed, the notion of measuring a solar cell by the ratio of the time it takes to extract and the time it takes to recombine is well known. In other fields, you can find people saying the mu tau product. And we'll see how important the mobility ratio is in our context. And we should remember that when we are discussing organic semiconductors, especially in the context of bulk heterojunction, then the morphology also plays a critical role sometimes. And the 2 points of for and against having a fine morphology are written here in this bottom box. So it's all a matter of give and take and finding the optimum and engineering a device that is working as good as we can. So let's see this thing about mobility ratio. So what I did, I took the Centaurus device simulator, which is standard in the industry, and I simulated a device which is an effective medium that mimics the bulk heterojunction. There is an anode and a cathode, and I chose a gap of 1.6 eV, an injection barrier here of 0.3 eV on either side, which are all somewhat reasonable. And then I said, let's see if we change the mobility ratio. So in this example, I'm fixing the mobility of the holes and I'm changing the mobility of the electrons. So you see, when the electron mobility is a quarter of the hole mobility, we have this red curve, and when we make the two mobilities the same, we get the blue curve. So obviously you can see that the fact that the mobilities are not the same is really hurting the device. However, for such a sentence to be true, you really need also to look what would happen if you change the mobility ratio, not by raising the mobility of the slowest carrier. What would happen if you keep on and raise the mobility of the fast carrier? So in this case, we are moving from the same mobility and we are raising the mobility for electrons. And look, the efficiency keeps on going up. So really the mobility ratio is not a bad thing. Low mobility is a truly bad thing. And I've listed here in the table the values that were extracted. A thing to remember is that when I ran these simulations, I've let the recombination to be exactly the Langevin recombination rate. But we all know that often in these devices, when you characterize them, you find that the effective recombination is lower, and it's often characterized by an effective reduced Langevin. So let's assume that we've managed to arrive at a reduced Langevin, which is through changing the morphology. Of course, morphology is a general name also for the chemical structure of the molecules, but it's not the mobility. It's something else which is not necessarily directly related to the mobility. And let's look at the case where the combination is a lot lower. So of course, all the values are higher. Now we are passing the 10% efficiency. And you can see again that there is this big shift from taking something which has one of the mobilities being too low, taking it up. But then if we keep on going, you see that a factor of 2.5, there is no difference between the blue and the green curve. Only when we go well above a factor of 10, we see a loss in efficiency starting to form. And really, if you have one of your charges with a mobility of 4 times 10 to the minus 4, how likely it is that the other one will have more than an order of magnitude mobility, considering the materials that we have today. So really, this issue is not so critical. And what else can we do when we are working with these devices or materials? We'll see that in the next slide. But I've again summarized the differences in efficiencies as a function of the mobility ratio. So now we are looking at an improved device. So we are done with the material structure, mobility, etc. And all we are doing now, we are taking the same device as before with the reduced Langevin factor, and we are adding blocking layers. And again, the first thing that we see is that there is a jump in the efficiency values. Now we are at 17. And for the sake of the discussion, I've also added here the percentage of the efficiency relative to the maximum efficiency that is found for equal mobilities. So really, you can see that again, low mobility is a bad choice. But if we are raising the mobility, look, a factor of 5 of the electrons being too fast, we're at 95% of the maximum value. So really, make sure that the mobilities are high enough, and this is what's important. And the next thing you must take care of is the device structure. All this thing of the mobility ratio, unfortunately, is a myth. And if you look at the original paper, the thing that changed there is the low mobility was going up. And if you are thinking, okay, I'm making a device where the recombination is a lot lower, so we'll reduce it by a factor of 10,000. So repeating the simulations, of course, will result in higher efficiencies. But in terms of the percentage, you can see that the lower the recombination, the less the performance sensitivity to the mobility ratio. So really, the take-home message is make sure that your slowest carrier is not slower than 5 times 10 to the minus 4. And then you need to take care of the device structure. This is really critical, and in other presentations I've dealt with different ways of making proper device structures. And you should always remember that what goes under morphology is always important, and this could be the recombination lifetime of the city states. This could be actual morphology, the bulk heterojunction morphology. But really, the mobilities, just don't make them too slow. So having made this one myth go away, I'll try in the next presentations to touch other issues, some myths that are taking root, and I've listed them down here. One is to do with the perovskites, the other about what's happening in organic in terms of recombination, and of course some of the measurements that we do, thinking that we are really extracting inner parameters of the materials, are not always like that. So see you next time, and thank you for listening.